So in this derivation, we are focusing on series LCR circuit containing, of course, your resistor, capacitor, and inductor. Say the capacitor inductor is fixed. Say we have a radio which has a fixed inductor and a capacitor value, fixed L and R, L and C actually. Now, when you switch this on, right? When you switch this on, what radio station will it tune to? That's what we are trying to figure out. Given a L and C value, what station will it tune to is what we are trying to derive. So the heading is resonance in series LCR circuit. So you're looking at the mathematical aspect. It is to derive the expression for the resonating frequency for a given combination of inductor and a capacitor. Typically, we have parallel LC circuit in a radio, and when we tune or when we change the capacitance of a capacitor, actually we get to change this. When you turn, right, we are changing the capacitance of a capacitor. What happens? Then the resonating frequency will change and we'll get to listen to different station. That's the whole funda. But here we are looking at, okay, you know what, fixed inductor and capacitor. You have a fixed inductor and capacitor, you don't have any chance of changing it. So this is not there, right? This is not there. You just have on and off. Right? When we just have on and off for a fixed LNC value, this radio will tune to a particular frequency. What is that frequency is what we are looking at. Now let's define it, right? Let's define the resonant frequency. The resonant frequency of LCR or your RLC circuit is the frequency at which the circuit naturally oscillates with the maximum amplitude. That's your definition, right? It's the same thing as what we discussed. Okay, now let's look at the derivation. So derivation, it looks something like this. So first we start off with R LCR circuit having a voltage of E and a frequency of omega, angular frequency that is, or frequency of F. Actually, let us do that. Let me continue now. So what we have here is the current amplitude will be equal to what? I is equal to E by Z, where Z is what? That's your impedance, and it's given by what? You have R square plus XL minus XC the whole square to the power of half. Now, for I maximum, for maximum current, let me write it in that manner itself. For maximum current, Z has to be minimum. So let's do one thing. So let's rewrite C square as R square plus omega L minus 1 by omega C the whole square. Let's differentiate this with respect to omega. That's the one which is varying, is it not? So we'll get 2z by, sorry, dz by d omega, which is equal to 0 plus resistance is constant. Differentiation of this expression will be something like this, times of L minus, so we have this to be, this will be plus 1 by 2 omega square L, sorry, not 2, my bad. This will be plus omega square C actually. Okay guys, now for or at point of minimum, right, we want this to be minimum at point of minimum. the derivative will be equal to 0. So 0 is equal to 2 times of omega L minus 1 by omega C times of L plus 1 by omega square C. Right, guys? So 2 and 0 will get cancelled and we have two expressions. Okay, if you solve both, you'll end up with the same answer, similar answer actually. So let's do that. So when you rearrange this, actually if you solve this, you'll get a negative answer, which is imaginary. Sorry, if you solve the second part, you'll get an imaginary expression. That's not what we have in mind. So that is not the right answer. So we'll take up, consider omega L minus omega C, that is equal to 0. So when you rearrange on all of that, you will end up with omega L is equal to 1 by omega C. So omega square is equal to 1 by LC, or omega is equal to square root of LC. And when we do express this, so I'll make use of R, I guess, resonance. So this would be root of LC, and finally we have, this is your expression for a given LC value that is connected in series. Your resonating frequency would be 1 by 2 pi root of LC. So if you have a device, radio fixed to a particular frequency, if they switch on, this is the frequency at which your station has to broadcast for that radio to pick up. Right, this set of words, we are converting that to a mathematical expression. Does it make sense? So what did we do? We started off with looking at our impedance. So we know that the impedance has to be minimum. That's the whole point of, that's the whole idea of resonance. So I used application of derivative. There are other ways of deriving this, but this is the way that I can think of as of now. So if you are not able to understand this particular part, you should be actually, you are in 12th grade. You guys have to be. So when we do differentiate it, we get this particular set of expressions, right? And when I equate this to 0 at the point of minimum, why am I equating to 0? This again is part of math that you need to understand. And you have your entire expression equated to 0. So for this expression to be equal to 0, this particular term has to be equal to 0. So we're considering that. The other term we can't consider because it leads to a negative answer, which is imaginary. So it's not possible. So as and when you solve it, we get the final answer. As simple as that.